Okay, so we start the first law of thermodynamics in chapter 19, and then we introduce different thermodynamic processes. So the first law of thermo is pretty much a version of law of conservation of energy, as it says here. Conservation of energy adapted for thermodynamic processes, distinguishing two kinds of transfer of energy, as heat and as work. So there's two ways we can transfer energy. We can put heat into a system and do work on the system. And relating them to a function of a body's state called internal energy. The law of conservation of energy states that the total energy of an isolated system is constant. Energy can be transformed from one form to another, but can be neither created nor destroyed. So you've probably heard this just in regular lay person way to say this is just conservation of energy. You can't destroy energy; it just transfers from one type to another, right? And then to give it more mathematical meaning, you write it something like this: for a thermodynamic process without transfer of heat, the first law is often formulated as du is q minus w, where du denotes the change in internal energy of a closed system. Q denotes the quantity of energy supplied to the system. So sometimes du will also be written as dE, delta E. So delta E or delta U. So then that's going to be delta U of the system. Or you know what, let's write it as, since we're mainly dealing with the gas, we can say delta U of gas, and that's going to be equal to the Q denotes the quantity of energy supplied to the system as heat. So you can say, you can write it as Q into gas. So that's how much heat you're supplying to the gas. And then W denotes the amount of thermodynamic work done by the system on its surroundings. So W is the work that denotes the amount of work done by the system or by the gas, right? So minus W by the gas. That's what it says here. An equivalent statement is that perpetual motion machines of the first kind are impossible. So another way to say the first law is perpetual motion machines are impossible. So that's kind of a weird way to say it, but it's another way of restating the first law. For processes that include transfer of matter, a further statement is needed. So we're basically transferring heat and energy, but not matter. So let's focus on that. On my formula sheet, let's see how I wrote it. Test is probably on test before it does. Delta E of gas is Q into gas minus work by gas. Yeah, actually I wrote it the same way. Delta E of gas is Q into gas minus work by gas. Another formulation I like is also to take this and put it on the left side and isolate the Q. Q into gas is delta U of gas. I'm going to write it, I think I like E better. Delta E of gas plus work by gas. So I kind of visualize it like this. I say, okay, there's a piston here. Okay. And imagine that that there is a gas here. So now if I put a flame here underneath the piston, so the flame will put heat into the gas, right? So that's, you're putting in heat, and then what's gonna happen? By putting in heat, the gas molecules are gonna now vibrate quicker. So it's very likely that their internal energy increases. Why? Because their temperature increases. When their temperature increases, their internal energy increases, because remember, temperature is a measure of the kinetic energy of molecules. So then, therefore, their energy would increase when their kinetic energy increases, right? But besides that, the gas is likely to expand, and if the piston is movable, the gas is gonna do work. It's gonna push the piston, right? And it's gonna do work on the system. So, so let's say if you pour in 100 joules of heat, let's say the internal energy of the gas increases by 60 joules. And then of course, the work done by the gas has to be 40 joules, right? So that's what that is saying. If you put in 100 joules of heat into the gas, it's gonna do 60 joules of work. Let's say it does 60 joules of work. Therefore, let's say it does 40 joules of work, and then the internal energy will increase by 60. We could now turn this around and say, oh, okay, nobody's putting in heat. Instead, imagine you pushing down on the piston. Okay, so now the piston is going down. And so now you're constricting the volume that the gas has to occupy. What's gonna happen here? Does the first law still obey? The answer is yes. You know, this isn't the only scenario where this is applied. Here, you're pushing down, you're not putting in heat. So the work by the gas is negative if you're the one pushing down on the gas. You see? So the work by gas is negative. So then what's gonna happen? Probably in this case, it might be better to imagine it like this. Take the W back to the other side, and then to say delta E of gas is Q into gas minus work by gas, right? So bring this to this side, and now write negative work by gas as work on gas, right? So negative work by gas is work on gas. That's always true. So if the gas is the one doing negative work, that means you're the one doing positive work on it. You see, like that. So now write this as Q into gas plus work on gas. And I could also, since I'm not pouring in heat in here, what's likely to happen is as you push down, heat probably is gonna pour out of the gas, right? So I could also rewrite it like this. Negative Q into gas is equal to Q out of gas. So now the gas is gonna exchange heat with its surroundings. You see? So now write this as delta E of gas is work on gas minus, write this as Q out of gas. Or you could even take this and put it on the opposite side. It's just you're playing with the equation, essentially. You're saying work on gas is equal to delta E of gas plus Q out of gas. Okay, so now I can say, let's say you do 100 joules of work. You push the gas down. Let's say the internal energy of the gas increases by 40. So this is 40. How much heat escapes from the gas out to the atmosphere? So then I can say 60 joules of heat escape to the atmosphere. You see? So now you draw the arrow depicting the direction of the heat that is out, that is going out. And so 60 joules of heat escape from the from the gas to the atmosphere. Or I could even make it similar to this one. I could say the delta E of the gas is 60. This is 40. So I can make the numbers the same, except the scenario is completely different. Here, I'm pouring in 100 joules of heat into a gas, allowing the gas to expand. The internal energy of the gas is increasing. In both cases, the internal energy of the gas is increasing by 60. Here, I am doing work on the gas, right? The internal energy of the gas is also increasing by the same amount, but 40 joules of heat is escaping. So at the end, the temperature of the gas is going to be the same in both scenarios. Here I'm doing work, some heat escapes. The gas heats because I'm doing positive work. Here, the gas heats because I'm pouring in heat. At the end, it's the same. Now, is it possible that some different scenario happens here? What if 140 joules of heat escape? So then you could have 100. If 140 joules escape, then delta E has to be what? Negative 40. Oh, so now the gas is going to cool down. You see? So that's kind of a weird scenario that you would push it in, but a lot of heat escapes. And because a lot of heat escapes, the gas is to cool down. So you might say, well, why did a lot of heat escape? Well, we don't know. The problem might just say a lot of heat escape for some reason. But as long as this sum of these two is this, then you're obeying the first law. You see that idea? You could even have a scenario where you could push on the piston. You could do 100 joules of work on the system, and you could pour in heat with a flame. Let's say you do 100 joules of work and you pour in heat. Let's say you pour in 100 joules of heat. Now what's the change in energy of the system?
200.
Yeah, now 200, right? So you're pushing it down. The gas is occupying less volume, and on top of it, you're pouring in heat. So as long as you decide which form of the equation to use, it doesn't really matter, but stay consistent. I like this one. I can say Q into gas in that case is 100. Delta E of gas, I don't know. And then work by gas is negative 100. And then the 100 goes over there. Delta E is 200. You see? Or you could use this version. So any of these versions is okay, you know, work on gas. But when you write it down, make sure it's making sense. If you do work on the gas, the internal energy increases, Q out of gas, then it should be here. You see? So as long as you're consistent, you're not gonna make a mistake. So in this case, the gas is really, really gonna heat up, okay? The first law doesn't only apply just to gases. Even though our emphasis is on gases, it could apply to solids and liquids, of course, also. So just like we learned in chapter 17, when you put in heat into a solid or a liquid, its temperature rises, and it also expands, right? So we could also apply this law to solids and gases. So let's say you have a rod, and then you put a flame, the heat, or you could have a bucket of a beaker of water. You put in heat. So we say Q into rod is delta E of rod plus work done by rod. Or we can say Q into water is delta E of water plus work done by water. Well, in that chapter we learned that when you heat it, it expands slightly, right? So the rod is doing some work against its environment, and the water is also expanding slightly. So it is doing some work, but 99.99% of the heat you're putting in is going to internal energy increase. The work that the liquids and solids are doing is very minimal compared to the internal energy increase. Why? Because they don't expand a lot like gases do. So we could more or less ignore this. So most of the percentage of the heat, 99%, goes into internal energy increase. That's why with with solids and liquids, you don't see a lot of people applying the first law, because it's this goes into here and this is ignored. You see, so we can say negligible. And then you can use the equation delta E is equal to, so we define something known as specific heat. Specific heat is defined as 1 over the mass dE dt. dE dt. Or I should say, let's see, how should I say this? Yeah, so the specific heat's definition, this is definition, is how much internal energy increase it has divided by the temperature change. You see? And then divided by mass. So for liquids, we define it that way. So we say delta E is mc dt, and then for the most part C is constant, and then we integrate it. We get mc dt is dE. So then we can say Q into rod is mc delta T of the rod. So that's kind of this that we have been using, this equation that we've been using is already an application of the first law of thermo. We're saying when you put in a certain amount of heat, all that heat goes into change in temperature for a solid. Even though it does slightly some work, we ignore the work that it does. So the amount of heat you put in directly goes into increasing its temperature based on whatever the specific heat of that solid is. And we could do the same thing with a liquid. We could say C is 1 over define M for the liquid, dE dt, and we could say dE is equal to mc dt, integrate, and we can say Q into rod or into water is mc dt. Or we could also define molar specific heat of a solid and liquid. It doesn't have to be, this would be called mass specific heat. Molar specific heat would be 1 over N. But it's not very used very often because for solids and liquids, we usually don't care as much about the moles of the solid and the liquid. We care more about the mass. But you could do N. then that would be N would be, then you would put here N, but then this would be the molar specific heat. Then this would be like this, like this. I'm not sure if in that chapter did we do a practice of converting from regular specific heat to molar. If we didn't, or even if we did, we can practice that again. So let's say water, specific heat of water is 4.184 joules per gram Celsius. If I wanted to calculate the molar specific heat of water, molar, what would I do? I would just say I would say 18 grams of H2O is 1 mole of H2O. And that would cancel. And that would just be 18 times 4, something like 72 or 75, depending on 0.18. Yeah, it looks like it's gonna come out around 75 joules per mole Celsius. Close to that. Yeah. So that means you would take 75 joules of heat to increase the temperature of 1 mole of water by 1 degree Celsius. So if I wanted to convert any of the other materials like a metal, aluminum, molar, you would take the specific heat of aluminum. Let's see, what is it? I think it's 0.215. Yeah, 0.9. So the 0.9 joules per gram. Now the molar specific heat of water is not necessarily going to be the highest because remember how we said the specific heat of water per mass is the highest, but per mole it's probably not, because aluminum, well, aluminum is not one of the real heavy ones. 27 grams is 1 mole. So 27 grams is 1 mole. So that's, yeah, now that's kind of bigger, times 27. Okay, 24.3 joules per mole. Now it's actually not that far from the specific heat of water, you see. And if we did the heavier metals, they might even be bigger than the water's molar specific heat, you see. Okay, so now you can kind of see that this equation, Q into rod, we can do MC delta T or NC delta T, okay? So technically speaking, for water, for rods and for water, what are we assuming? When we're saying that the work done by the rod is negligible and the work done by the water is negligible, we're assuming that when you're putting in heat, the volume is more or less stays constant. Even though it does expand, we're saying it's negligible. So we're saying when you pour in heat, the process is isovolumic for rods and liquids, because their volume increase is negligible. So we could now put V, specific heat at constant volume. You see, isovolumic. So this specific heat of water is isovolumic, isovolumic, isovolumic. So more specifically, we should have a V in the bottom. So now we get to gases and we say, oh, definitely when you pour in heat, the volume can expand greatly, right? So let's define some different processes for gases. So the first one, let's do isovolumic. So how can you accomplish an isovolumic process for a gas? For a gas, you would have to have the intention, let's say you have a piston, you would have to lock the piston, The container, in other words, has to be such that the piston is unmovable. Or it could even be this room. I can pour in heat into this room, and of course the walls aren't going to move, and therefore the gas in this room is isovolumic. And if I put in heat, all the heat that I put into this room, let's say if I turn on the heater, all the heat I put into this room will go into the temperature of the gas heat increasing versus the gas doing work. You see?
So isovolumic is just constant volume?
Yeah, constant volume. So the way to accomplish constant volume for a gas would be don't allow the piston to move, or just have a room that is enclosed, a box that is enclosed and whose volume cannot change, you see. So now you put in heat. And then what does the first law say? Well, Q into gas is delta E of gas plus work by gas. So by forcing the gas to not do work, not allowing it to do work, the W of the gas is 0, and it behaves like a liquid or a solid, right? So now all the Q into the gas goes into the internal energy of the gas. So then we can say, now define something known as CD of the gas, which is 1 over N dE dt. So same thing that we did for liquids and solids, right? So then this is going to be NCV delta T. Okay? Now, what's the PV diagram of that gas going to look like? So with solids and liquids, we don't really draw PV diagrams as much, but with gases, that's one of the common things to do. Draw PV diagram. Why pressure and volume is the most common one to draw? Because remember, pressure times volume gives you units of what?
Joules.
Remember we discussed on Monday, it has very important units of joules. So by drawing pressure versus volume, not only do we have an idea of what the pressure and the volume are doing, but the area under that graph is the work done by the gas. It's the joules, right? So we do usually pressure on the vertical axis, and you could do either atmospheres or pascals, right? So let's say pascals. As a review, just remember that 1 atmosphere is sea level pressure, and it's equal to what? 101.3 kilopascals. So it's a 101.3 times 10 to the 5th pascals. Or it's equal to 14.7 psi, pounds per square inch. And a pascal is a what? The pascal is a Newton per meter squared. So it's the metric units of pressure. Remember, pressure is defined as force over area. Force over area. So pounds per square inches, you could write it like this. That's the British unit system way of writing it. And then pascals is Newton per meter squared. And this is atmospheric sea level pressure. So you could write as 101.2 kilopascals, or write it as a scientific notation. So for isovolumic, what is it going to look like? So if we start at a certain volume V1, right, you're putting in heat, but you're not allowing the volume to increase. So the pressure is just gonna increase, right? So if it starts at P1, the final pressure P2, you're putting in heat into the gas. So the pressure will just increase as I put in heat, the pressure will increase. Why? Because the molecules will be moving faster, 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 right? And all the heat you're putting in is going to how fast they are moving, okay? The next thing to discuss is to say, what is CV of a gas? What is CV of gases? Okay, whereas with solids and liquids, there was no general way for us to say, oh, the C of a solid or a liquid is this. We had to simply just go to a table and we had to look what the C of that solid and liquid was, particularly because for solids and liquids, we were doing specific heat per kilogram or gram, right? But for gases, we're gonna tend to do the specific heat per mole. And there's a more general, predictable pattern for gases, depending on if the gas is monotomic, diatomic, polyatomic, right? So there's gonna be a more predictable pattern. So we can say, what is the CV of a monatomic gas? Well, it gives you the answer here. 3 halves R. 3 halves R. R is the gas constant. The energy of a single monatomic gas, 3 halves kT, noble gases. The CV of a monatomic gas, you see, it's very predictable. So it's not like it's not even asking us what monatomic gas is it, because helium is monatomic. Monatomic means the gas molecule is not bound to something else. So helium is just He. Hydrogen will be diatomic. It comes as H2, right? So what other gases are monatomic? Argon, I believe, is monatomic. I think neon is a monatomic gas. So that the typical one we use as an example is helium, but there's other monatomic gases. So it says that CV is 3 halves R. So what's the units? Joule per Kelvin, or you can say joule per Celsius per mole, you see, instead of per grams. So CV of gases, so for monatomic, CV is 3 halves R. So 3 halves, what was R? 8.314, right? The gas constant. What was the units of the R? TB is nRT, which is nKT, right? So what was the units of the R? Well, this is joules, remember? So per mole per Kelvin. This one has to be Kelvin, can't be Celsius, right? But then when you get here, CV is 3 halves R. So 3 halves obviously doesn't have units. So something that has no units times R, it's gonna have the same units as the R. So then it's just 1.5 times R. So 1.5 times 12.47.
Could you repeat that last part?
Yeah. Joules per mole. Now this one can be Celsius or can be Kelvin, either one. You see, so notice that the molar specific heat of gas, monatomic gas, is a lot smaller than water was 75, right? And aluminum was 25. So gas should be able to heat up much easier. So it means you have to just pour 12.5 joules of heat into a monatomic gas for 1 mole of that gas to heat up by 1 degree Celsius. That's what that means. If you put in 12.5 joules per 1 mole. That's if you're forcing the volume to not increase, right? So if all the heat you're putting in is going into the molecules moving faster, you see? So you only have to put in 12.5 joules of heat to increase 1 mole of that gas. Question?
I forgot.
Yeah?
Yeah.
Probably I answered it already. Now where does this come from then? What's the proof of that? 3.5. Well, let's go back to the definition of CV. What is CV? CV is 1 over n dE dt, right? That's the very definition. 1 over n dE dt. So in other words, how much heat, how much energy is increasing. In other words, it's a measure of how much the temperature increasing per unit increase in internal energy. Or I can say it the other way. How much the internal energy is increasing per unit increase in its temperature, per mole, I guess, you see. For a monatomic gas, the gas is not bound to any other molecule, right? Let's say it's got helium. So the other day we proved a certain equation, PV is equal to 2/3, I think, what was it, kinetic energy? Something like that. Remember we did that box thing and with the molecule going back and forth? And kinetic energy was?
It's 3 because it's 3 dimensions.
Yeah, but was it 3/2 or 2/3?
It's 3-2.
3/2?
Yeah.
It's 1/2.
Yeah.
1/2 mv squared. No, it's meant to.
Wasn't it 3/2?
Yeah, that's in 3D.
Huh?
That's in 3D.
Because that's the part that was kind of confusing me because when we had a
Yes.
KE,
What is KT?
1/2 mv.
Yeah, and then you got PV is equal to 3/2, and then kinetic energy is 1/2 mv squared. No, you know what? I think it was
Yeah,
2/3.
Yeah.
I think it was 2/3 because what happens?
Yeah.
KE
Goes
is
the other
equal
way.
to 1/2
KE is 1/2 mv squared, 2 cancel, and then V squared is equal to 3 PV over M, and then PV is equal to nRT. Yeah, and then you get square root of nRT, and then this is equal to 3, and then that's equal to the RT over the molar mass. Yeah, that's right. So remember the root mean square velocity is 3 RT over M. So you can kind of, if you're stuck, you can just go rederive it anytime if you're understanding it, right? So it goes, PV is 2/3 kinetic energy. Kinetic energy is 1/2 mv squared. The 2's cancel, you get 3 on the bottom, and then the 3 goes up to the top, and you get PV. Then you bring in ideal gas law and RT, and then that changes to molar mass. Oh, so what was my point? Where was I going with this? Oh, monatomic gas, all the internal energy of the gas is going to be in the form of translational kinetic energy. See, this is the translational kinetic energy of the molecule, right? This is, we can call this translational kinetic energy, half mv squared. Monatomic ideal gas is going to be almost like imagine a ball, right? Imagine a ball that's just going like this, and then all its internal energy is in the form of translational kinetic energy. You don't have to worry about rotational kinetic energy. Diatomic gas, we're going to introduce in a minute. With diatomic gas such as H2, you have to visualize it as two balls stuck with a little rod. So now not only can it translate in the x direction, the y direction, and the z direction, but it has moment of inertia from physics 1. It can rotate around this axis, so it can have rotational kinetic energy, and it has another degree of freedom. So in the x direction, y direction, z, it could go like this, and it could go this axis. It could go like this. So it can have this kind of rotational energy and this kind of rotational energy. You see, like that. So this way. But with monatomic gas, only translation. So in other words, the idea is that with the monatomic gas, the energy is only translational kinetic energy. Okay? Okay, therefore, here comes the idea. Let's write that equation again. PV is 3/2 kinetic energy. PV is equal to nRT, right? The other day we proved PV is, so focus on that. Or is it 2/3 or 3/2? Oh, it should be 2/3, yeah. Because this is 1/2. So the two should cancel, right? So that's how you remember it. So you have 2/3. So now PV is 2/3 kinetic energy. But now look at here. dE dt. For a monatomic gas, the internal energy is equal to the kinetic energy. So it's dKe over dt. So take the derivative of this with respect to this. And you get what? In other words, an incremental increase in its kinetic energy, small incremental increase in its kinetic energy, yields how much temperature increase? dt is that. Or you could say vice versa, an incremental change in its temperature yields an incremental increase in its kinetic energy. So now the CV is 1/n of the ratio of this to this, right? So then if you take this one down here, you get 3nr over 2, right? dKe dt, right? Take the 3 over there, 3nr over 2. So now CV is going to be what? 1/n of what? dKe over dt. Nice.
So we
The n's cancel,
3 over 2
and voila, you have 3/2 r. And n cancel. So all that stuff that the other day we proved, the 2/3 stuff, was very, very crucial. Because then it connects kinetic energy to PV, and then if it connects to PV, it also connects with nRT. So now if you do the incremental increase in this, incremental increase in this, and then CV is the ratio of how much kinetic energy increase yields how much temperature change, right? Then you do this 1 over n, and you get 3/2 R. And that's the CV of monatomic gas. Okay, so maybe from there the best thing to do is to go to isobaric process. Okay? Then we're gonna go to diatomic gas. So far the conclusion from there is for isovolumic process, what's the conclusion? Q is equal to what? NCV delta T. Because delta E is 0. I mean, sorry, the work done is 0. If you want to write this in a derivative format, you say dQ is NCV dt. And then the graph looks like this. The PV diagram. The gas is doing no work. And then CV is equal to 3/2 R for monatomic. Now, isobaric is going to be what? Constant pressure. So, the PV diagram is going to look like this. You start at a certain volume, at a certain pressure, and you put in heat into the gas in such a way that you allow the gas to do work but not increase its pressure. Okay? How would you accomplish something like that? Not increase its pressure, but you allow it to do work.
Increase the volume.
Huh? Today's lab we're gonna do like that. We're gonna do isobaric. It's actually pretty easy to do. You just take the gas, you put it into a hot container, and then heat comes in, and then the pressure is constant. It's like something like this. You take a gas, let's say it was in room temperature, and you put it into a hot bath water. Yeah, let's say the bath water is 80 Celsius. So you pour it, you put it completely in the water. And then here's the piston. And then maybe you put a certain weight on the piston. And then as the gas is doing work on the piston, you don't lock the piston, you allow the gas to expand. So as the gas is doing work on the piston, pretty much the pressure stays constant. So it expands to some pressure. I mean, it expands to some volume, and you're gonna see we're gonna create a PV diagram on the Explorer, and it's gonna be like that, straight line graph. Or you could put it in a cold bath, and then the opposite will happen. It will go from a bigger volume to a smaller volume. It will contract, and then heat will escape.
But for that to happen, the weight has to remain above water, right? Because of buoyant force, or would that alter the
Yeah.
that would make the pressure consistent. The weight would have to be
Yeah.
consistently above.
Yeah, today, in today's thing, we have something like this. The gas is connected to a tank, and then you have air, and then here you have a piston. You have a piston, and you could put weights on the piston here. And then the tank of air is the one that you put in cold water and hot water. And then the air is connected to the air inside here. So the piston is you're not putting in water, that's true. Yeah. Yep. Okay, so in this case, what's the equation gonna yield? So the thermodynamics, Q Q into gas is gonna equal delta E of gas plus work done by gas. Is the gas gonna do work? Yeah, it's expanding. So, yeah, it's expanding, but it's expanding in such a way as the pressure is more or less constant. So this portion of it, Q into gas, this portion of it I can still write as NCV delta T. Right? Because that's the very definition of CV. CV is defined as 1 over N dE dt, right? But then this one I'm going to write as what? PdV, the area under this graph. The work done by the gas, right? The area under that graph, PdV. But since pressure is constant, right, what happens? Go to the ideal gas law. If P is constant, what happens? PdV can be written as what? It's like taking the derivative of this with this being a constant, right? So then you have PdV can be written as nRdt. So now we have here, let's write this as a differential. dq is ncv dt plus nr dt. Okay? Now what can we do? This is the change in temperature due to the internal energy increasing. This is the change in temperature of the gas due to the gas doing work. You see? So then what happens? Combine these two, and then you get what? NCV plus R. Now define something new, a new concept called a specific heat at constant pressure, right? Because what are we doing here? Isobaric, right? Isobaric. So define specific heat at constant pressure to be what? The change in internal energy over the temperature, or I should say change in, so change in internal energy at constant pressure at constant pressure, whereas the other one is at constant volume. Okay? So then what's that gonna be? CV, this thing is gonna be what? NCP. Right? And then Cp therefore is gonna be what? dq over dt 1 over n. So from this we can conclude what? Specific heat at constant pressure is Cv plus R. Right? Cv plus R. So for a monatomic gas, what was the Cv? 3/2 R, right? Which was equal to 12.47 joules per mole Kelvin. Now, what's the Cp gonna be? 3/2 R plus R. 5/2 R. So that means you're gonna do 5/2 R, 8.314. So that's gonna be 20.8. Okay, so this, let's see if this makes sense. If you're heating the gas, but at the same time, the gas is allowed to expand, it takes 20.8 joules of heat to increase the temperature of 1 mole of that gas by 1 degree Celsius. But if you're heating it and you don't allow the gas to expand, it takes only 12.5 joules of heat to increase the temperature of 1 mole of that gas by 1 degree Celsius. Do you get the idea? So it takes more heat to increase the temperature of the gas if you allow the gas to expand. Does that make sense?
Can you repeat that?
It takes more heat to increase the temperature of 1 mole of gas by 1 degree Celsius if you're allowing the gas to expand as you're putting in heat. Because the heat that you're putting in, some of it is going into, right? If you're putting in, let's say, 100 joules of heat, in isovolumic, 100 joules of heat, it goes into 100 joules of increasing its energy. But if you, in isobaric, you put 100 joules of heat, maybe 60 joules goes into increasing energy, 40 joules goes into doing work. The gas is doing work against the system, you see? So just by virtue of energy conservation, it should be harder because some of the heat you're putting in is going into moving the molecules faster. Some of it is going into the gas doing work. So it's harder for the gas to increase its temperature, therefore CP should be higher.
So should so are the molecules moving at the same speed then? Would they be moving at the same speed if we have this like side by side?
Well, it depends how much heat you're pouring in. So let's say you put in 20.8 joules at constant pressure for 1 mole. Yeah, they will increase by 1 degree Celsius. You know, so in other words, if I have two containers, one I don't allow to expand, I lock the piston. The other one, let's say this is 1 mole of helium. And let's say this is 1 mole of helium. This one I allow the piston to move. So now I put in 12.5 joules here. And I allow this one I pour in 20.8 joules. So this one is not going to expand. That means the temperature of this helium is going to increase by 1 degree Celsius if I lock the piston. Here, if the piston moves up and the pressure of the gas stays constant, what's going to happen? I put in 20.8 joules, the temperature will also increase by 1 degree Celsius. But here, if I only put 12.5 joules, you see, 12.5, this one will increase, its temperature will not increase by 1 degree Celsius. Maybe it will increase 0.6 degrees Celsius.
So yeah, then it would be moving at the same speed because it's we're saying that temperature is a measure of the kinetic energy of the molecules. So if 1 mole is increasing.
Yeah, so if you put in 12.5 here, the final velocity of the molecules here will not be the same as the molecules here.
It'll be less than that one, right?
It'll be less than that one there. Now the next question is going to be, what if you take isovolumic, lock the piston again, 1 mole of hydrogen gas, and you put in 12.5 joules. Lock the piston. And then now don't lock the piston, 1 mole of hydrogen gas. Let's say 12.5. Whose temperature is going to increase more? Well, if you're just asking whose temperature is going to increase more, it should be this. Because isovolumic should always increase more than isobaric. You see? But if you want to compare this to this, now what's the answer? It's not that obvious. Okay? If you put in heat into the helium, all of the heat you're putting in goes into translational energy. You see? If you put in heat into hydrogen, what should happen? Now, conceptually, the hydrogen should start moving faster this way, but it should also rotate faster and rotate faster this way, like the two dumbbells, right? But this rotation and this rotation do not increase the temperature of the gas. They just increase the vibration. Only this motion increases. You see? So the temperature of this should not increase as much as this guy. That's the idea. And the temperature of that should not increase as much as that guy. Because the rotational kinetic energy is not proportional to the temperature of the gas. Only translational is. You see? So then that's why we say now, molar specific heat of diatomic molecules.
So that it's not proportional, so to the vibration, just translational, right?
Yeah.
Then-
You see,
But energy is still, so it's energy still divided into it, but not at the same factor as
yes.
translational.
Yes. Let's see here. Okay, so you see here okay, so you see degrees of freedom. How many degrees of freedom does a monotomic gas have? So it's saying here the monotomic gas has 3 degrees of freedom. So each degree of freedom gives you 1/2. Remember the other day we showed that the kinetic energy is 1/2 mv squared. That's equal to 3/2 nRT. So then the conclusion was that 3/2 RT. So the conclusion was that each degree of freedom gives you 1/2 RT of energy. Kinetic energy, 1/2 RT per degree of freedom. So then this one it tells you monotomic gas has 3 degrees of freedom, X, Y, Z. So helium and argon. So CV is 3/2 R, 12.5. Now when they experimentally do this calculation, they get for helium 12.5, argon 12.6. So even though our prediction is that it's going to be 12.47, the experimental results are slightly off because of quantum mechanical complications. So our analysis is kind of simplistic and it only includes classical physics. You see. So then when you do diatomic, it's got a rotation, so it's like a dumbbell. So it's got X, Y, and Z, plus it's got moment of inertia around an axis like this. It's got energy, kinetic energy of rotation, 1/2 I, let's call this, let's say the Y-axis, 1/2 I YY omega squared, the rotational velocity omega, and the moment of inertia around there, right? And then it's got the rotation around that's the one that's coming out, let's call that the Z-axis. Rotation, this is the X-axis, this is the Z. 1/2 I ZZ omega Z. So if it's also rotating like this, around the z, this would be the y-axis. Around the z-axis, it'll be like this. Omega z, and then this one will be omega y. Now, why aren't we counting if it's also rotating like this around the x-axis? Why don't we count that? They're only counting 2 extra degrees of freedom. You see? So they're saying that it has 5 degrees of freedom. Because the moment of inertia going through the middle of the molecules, you see, so if you call that rotation around the, oh no, this is y-axis. The x-axis, if you call that the axis going through the middle, so it'd be like this, you see. So that one is gonna be a lot less. The moment of inertia, half Ixx. Ixx is much, much smaller than Iyy. And it's also much, much smaller than Izz. So to take a dumbbell, rotated around an axis, cutting it through the middle, is a lot easier than to rotate it like this and like that. You see? So it's negligible. This moment of inertia is negligible compared to those other ones. So we can ignore this. So this energy, these 2 energies are the primary ones. So then what does that mean? It's got 2 extra degrees of freedom due to rotation around the x-axis. They're doing, in this case, they're doing the x-axis and the z-axis. The one going through them, they're calling it the y-axis. And that one is negligible, they're saying. So each degree of freedom adds half a r to it. Okay?
Are we gonna go further into that, or is this just purely for the conceptual?
Pretty much, yeah.
We're just like looking at it, just to look at it, this.
Yeah, so it's just for us to know why CV for a diatomic gas is higher,
Yeah.
right? So then if you say CV, definition of CV is what? 1/n dq dt, right? And then you say dq is equal to, from the first law of thermo, dE plus work done by gas. So that's 0 for isovolumic. And then you say dE is equal to, from the equation that we had, PV is equal to 3/2 times kinetic energy, or is it 2/3? 2/3. So if you go to the derivation of how we went, we said PV is 2/3 KE, right? And then here you have PV is equal to nRT is 2/3 KE. dE is equal to kinetic energy of the gas. Let's do it like this, 3/2 R N dKE over dt. So you see where we did the other day, we said PV is 2/3 KE, and then 3 goes over there into the NR, and then the 2 comes down here, and then we take the derivative of this, we take the derivative of this, and then we say internal energy is just, for a monotomic gas, we say the internal energy is just kinetic energy translation, right? Okay, so here's what happens. For a diatomic gas, the kinetic energy now becomes not only the 3 degrees of freedom of translation, but it becomes rotation, right? Each of this has 2 more degrees of freedom of rotation, right? So then this becomes actually 5 halves. In other words, this equation literally changes to becomes 5. And you have 5 halves NR.
And so like in the previous, how we said, the translational, the X, Y, and Z, they're all equal. So same thing right here for the rotation on the translational, it's all equal, evenly distributed.
No, the rotation doesn't have to be, in other words, this omega doesn't have to be the same as
The translation.
that omega,
Or, yeah.
but they are, yeah, they don't have to be the same, but they do add, in terms of temperature, they do add,
That's why I would assume the 5 comes from, like, because.
in other words, the kinetic energy, oh, okay, here's a good way to put it. Here's what's happening. The reason why we have to change from 2/3 to 2/5 is because when these guys have more kinds of kinetic energy that they can have, but the extra kinetic energy that they can have does not change the temperature of the gas, only the translational changes, right? So this kinetic energy is the total kinetic energy. So in the case of monatomic, the kinetic energy is just pure translation, half mv squared, right? But in the case of diatomic, we can split this kinetic energy into translation plus rotation. You see? Now the rotation adds 2 extra degrees of freedom to the translation, so it ends up making it such that this is almost like a Physics 1 lecture. If you have, let's say, kinetic energy of translation is 1/2 mv squared plus 1/2 mvy squared plus 1/2 mvz squared. And then rotation is 1/2 Iyy omega squared plus 1/2 Izz omega z squared. But then if you take a ball, right, Iyy is gonna be the mass of this guy and the distance from here squared, right? So it's, treat the balls as like particles, and the mass of the moment of inertia of that is gonna be 2m times their distance from the axis squared, right? So you're gonna have 1/2 2m times this distance d squared times omega y squared. Same thing here, 2m d squared omega z squared. We're getting really into finite details here where Physics 1 is kicking in. So the mass times its distance from the axis of rotation squared, right? And then, okay, the 2 and the 2 cancel, then you have mdy squared plus md squared omega z squared. Now what's omega y times, let's see here, squared. What if we put them together? Omega y times d. We have there 2md squared. Omega y times d is what? Omega y was what? The angular velocity like this, right? Remember from physics, B tangential is equal to omega r. So if you take the omega y, which I defined as the angular velocity coming out towards you, right? You multiply it by that distance d, what are you gonna get? The tangential velocity of that ball coming out toward you. So we can call that here mvy, right? And then now the omega z, I call this omega, right? The rate at which it's spinning this way. So then this one can be vz. So the velocity vz this way, this vz, right? So then this is, you have mvz squared. So basically I took the moment of inertia equation from physics 1, doubled it, because each ball has a moment of inertia around the middle, right? And then I applied that to, then I made it look like the kinetic energy. Okay, so now what is that gonna be? Now add that to the translational kinetic energy. What do you get? Total energy is gonna be what? 1/2 mvx squared plus 1/2 mvy squared plus 1/2 mvz squared. And then I'm gonna have what? V tangential is gonna be the one coming out toward you. So then that's mvz squared plus, and then the other one we'll call mvy squared. But this one is negligible, this moment of inertia. You see? So now if you add that, you get what? You add another 3/2. The Vx doesn't change. But the more easy way to say it is that you've added what? You've added, let's see here, 1/2 v squared. This is 1/2 v, this is 1/2 v squared. This is, this is, what was I trying to say? 2/5.
Yeah, because we were trying to figure out, because before, since it's, with the 3/2, they were all equal, so now with the, other two, should they all be equal to the energy?
In other words, I'm trying to argue that where's the 2/5? What's the real detail? Why does it go from 2/3 to 2/5? If I could prove that, then I can say, okay, the CV of the gas has to be higher by that same amount. In other words, what's happening is that I'm adding 2 rotational kinetic energies, right, to the 3 kinetic energies. And those 2 are increasing the total kinetic energy, but they're not increasing the temperature. So in order so that the temperature doesn't change, PV is nRT, right? If the temperature is not changing, but I'm just adding rotational kinetic energy, I have to fix this number so that it cancels that extra. Okay, so then that's what basically this is gonna be 1/2 RT, and then this is gonna be, 3/2 RT, this is gonna be 1/2 RT due to this guy, and then another 1/2 RT. Because each one is adding a degree of freedom, right? And now this is gonna be the 5/2 RT. In other words, the temperature is not gonna change. right? It's gonna stay whatever it was when it was 2/3, you see? So then when you take this and you do that analysis, let's see here, dq is equal to dE plus PdV, so this is cancels. dq is equal to dE, so then it's equal to 1 over mCV kinetic energy. Now I'm kind of all over the place. Okay, dq is equal to nRT. So we said dEd kinetic energy. Okay, you know what? Let's just leave it as Cv is equal to 1 over n dq dt. So then, since you're adding 3 degrees of freedom, it's just going to be 1 over n 5/2 nr dt over dt. So then this cancels, and then Cv is equal to 5/2 r. So basically, you're just saying 3/2 r plus add a half r plus add a half r, and you get 4/2, 5/2 r. So let's say diatomic gas N2, it takes 20.7 joules, an oxygen, 20.7 joules or 20.8 joules to heat up 1 mole of oxygen by 1 degree Celsius. So now that's getting higher. It's getting kind of what aluminum was for the metals. Okay. Now, what's the Cp of the diatomic gas? Well, that one we can just use the general equation. Remember what was Cp? Cp was Cv plus R. It was always harder to heat up at constant pressure because you're allowing the gas to do work. So then that's just going to be, you add another extra R to that, that's going to be 7/2 R. So this is for a diatomic. Okay, then you go to polyatomic. So then you add what other degree of freedom? Well, if it's a polyatomic like NH3, CO2, H2O, right? Polyatomic, CO2, H2O, NH3. So basically anything like 3 or 4 molecules. You're adding at least 1 more degree of freedom, because then you can rotate in the X direction, Y direction, or Z direction. And in some cases, you also might add 1 more degree of freedom due to vibration, a vibrational energy. So then it could be 7/2 R or 6/2 R. So either 6 R or 7/2 R. And of course, the Cp will just be 1 R bigger than that.
So as the molecule gets bigger, does the vibrational no longer becomes negligible, like with the diatomic?
You could also have diatomic where the vibrational kicks in if you make it hot, at hotter temperatures. Yeah. But right now, just this consideration, they're not including vibrational. They're just doing the rotation. So 7R or, so then if the Cv is 6R, the Cp will be 7R, and then this will be 9/2 R. So let's just take, for example, water, steam. What is the specific heat of steam? You probably remember from doing the problems in that chapter that we're on. 2010 kilojoules per Celsius per kilogram, or you could just say 2.01 joule per Celsius per gram. So steam is, of course, gaseous form of H2O, right? 2.01 joule per gram Celsius. Okay, now if we wanted to do per mole, we would say 18 grams is 1 mole. 18 times 2, okay, pretty much 36 joules per mole Celsius. So steam, which is H2O gas. Okay, let's compare, obviously it's gonna be polyatomic, and then this one is gonna be the CV, right? Usually the ones that we use are the CVs, not the CPs. So it's either 6R or 7/2 R. I mean, sorry, not 6R, what was the other one? I think I wrote that wrong. It was 6/2 R, I mean. 6/2 R. I guess we could just write as 3. So what they're trying to do by writing it as 6/2 R is to show you the progression, you know, 6/2 R or 7/2 R. And then if that was 3R, it would be 4R here.
And you said it was 6 because it's now not negligible on the x-axis?
Now no longer negligible in the X, so you add another 1/2 R. You keep adding 1/2 R every degree of freedom, you see. So, so then you have this. So if we wanted to see which one water is, remember R was 8.314. It looks like it's probably gonna be 8.314, maybe 4. 4 times 8.314, 33, 4.5 times. Okay, it looks like it's around, it's between this and this. It's not quite either one, because 4R, or actually I should be checking this one, right? Not the CP. CV. Oh no, CV comes out 29 joules. If I do this one, I'm getting 29 joules per mole Celsius. It's not even, doesn't even match. So is it possible we're using the specific heat at constant pressure? Specific heat of steam at constant, so I guess we have to be specific. Let's see. Specific heat of steam at constant volume. Okay, this website is a more careful how it's doing it. Specific heat at pressure and heat, CP, CV, and it gives you even British thermal units per pound per Fahrenheit, and then it gives you the ratio, because we're going to talk about that Monday. The ratio of the CP to CV is a very important quantity that is going to be interesting, and then of course CP minus CV should be equal to R, right? So if you subtract them, it should be equal to R, but I guess they're using different units. So anyway, so let's go to here for air. CP is 1.01, CV is 0.718. So let's just go carbon dioxide. Why is it so small, 0.844? Kilojoule per kilogram, joule per gram. Oh, this is per gram. I thought it would give us the molar specific heat. I want something to give me the molar. I should say molar. That's why it wasn't correct. Molar specific heat of steam. But still doing it per gram. Let's see, Fahrenheit. I guess it's changing based on temperature also, because all our considerations were assuming that CP and CV are constants, and even that's not true. So, so let's see here, water vapor. I guess if you want to say steam, because you could have water vapor below 100, right? So if you want to have boiling water, it would be above 212 Fahrenheit, right? So let's say 250, 1.855 is the CP. That's the first one that's like, no, hold on. What's boiling? 212? 212 Fahrenheit is boiling. Okay, so the first one that they're giving 1.852. So if we want to convert that, it would be what? So CP of steam at 225 to 12. Actually, even 200, even this one is already steam. No, this one is the steam, 225. 1.852. That's joules per gram Celsius. Now multiplied by 18 grams to check, that would be the molar specific heat. Because I want to see the one that we're using, is it CP or is it CV, this one that we've been using in the past chapter. If you do 18 times there, what do we get?
33.336.
33.336. Even that's not what we've been using, it's less, right? So then from there, is that 4R or is that 4.5R? Because I want to see what water is.
It's closer to 4.
It's closer to 4?
Yeah.
Oh, okay. So that means for water, you have only 6 degrees of freedom, this one. But of course, as you're increasing, maybe eventually, you see how high this is getting? 1.852, 1.887. Eventually, if you get to 1200 Fahrenheit, let's say 2000 Fahrenheit, you see what's happening? As you get to very, very hot, 2000 Fahrenheit, 2.836. So now, of course, if we convert that to molar specific heat, we're going to get values that's even more than 4.5R. So more degrees of freedom are coming into play. So of course, it's going to take more heat to heat up a steam that is at that temperature than the steam that is at a colder temperature, you see? Because when you're putting in heat into it, its motions is so complex that it's going into that motion and less of it is going into translational energy. You see? So that's what it means to say the specific heat is getting higher, because it's harder to heat that object. It has more ways of storing energy than just translation. Well, it's kind of hard to explain all this. I tried my best. Try to think about it, see the video again and again. Okay, so we'll do the lab. Let's go about a 20-minute